So the topic today is number theory. So what exactly is that? It's like a topic in math that deals with like stuff like prime numbers and um, like greatest common denominator, and that's like the stuff that we'll cover. So let's get into it. So I think you should all have the link to the slides. Put in the chat. Yeah. So the first thing we'll cover is the Euclidean algorithm, and what it is a algorithm for determining the greatest common denominator of two numbers, and it does it in a very efficient way, and we'll start looking at that now. So what is the greatest common denominator? It's the largest integer that divides both numbers, right? And this can also be extended to more than two numbers. If you have like n numbers, then the greatest common denominator is the largest number that divides all those n numbers. And we'll see that using just this algorithm, you can also find the greatest common denominator for all n numbers. So the first thing you should do is when you try to find the greatest common denominator is you divide the larger one by the smaller one. So here we do that, right? And we write x equals to a times y plus r, right? So x is so a is what you get when you divide x by y, and it's the floor division, right? The regular integer division when you like write a program. That's what a is. Like so, I use the Python symbol here, so we know what exactly it is. And x and r is x mod y, so there's also the Python symbol. So the yeah. So if you find that r is equal to 0, then y has to be a GCD, right? Because no larger number than y can divide y, and y also divides x. So that's clearly the largest, the greatest common denominator. And this will be like the base case in this algorithm. So it's like a recursive algorithm, and when you find that y divides into r, then that's like the base case. So in the general case, we know that g, which is the greatest common denominator, has to divide both x and y, right? Just by the definition. And if you look at r in the expression, r is just a linear sum of x and y, right? And x and y are both divisible by g, so therefore r must also be divisible by g. And if r is divisible by g, then we know that the greatest common denominator between y and r has to be the same. And why is that? It's because we know that g divides into r, and if any other number divides both r and y, then that number clearly also must divide x and y. So therefore, we know that g must be the largest integer that divides r and y. So now we've reduced this to a smaller problem because r has to be less than y since it was a remainder, right? So because we've reduced this to a smaller problem, we can use recursion on it, right? And the base case we know is already when r is equal to 0, which means that y divides into x. And we also have to have a special case here where y equals 0. So when you actually program this, you don't want to divide by 0, right? So if y is 0, we need to have another special case there. And there, the GCD is just for when y is equal to 0 is simply x. But that's just a special case. Other than that, like this is basically the way the algorithm works. And so we can use this to efficiently compute the GCD, and the runtime is basically the number of digits in B, which is like log B. And we can prove this. The proof of this is actually pretty interesting. It's like what you do is you say if like what are the two numbers that what are two smallest numbers for A and B? Or sorry, what are two smallest numbers for X and Y that require n steps? And it's actually the nth terms for the Fibonacci sequence. And since the Fibonacci sequence is exponential, we know that the inverse of that, which is logarithmic, we know that the GCD grows at a logarithmic pace. It's not that important. That's why I didn't include it in here. But if you are interested in finding like why is it efficient, like why is it only take logarithmic steps, I'm sure you can look it up. Let's see. Before we go on, I'll just do like a quick poll. If anyone has any questions, you can type in the chat. Let me find this poll. Yeah, so I'll launch the poll. If you have any questions, you can type in the chat or just unmute yourself and ask. If you want me to explain something again, or you don't think it was clear, you can tell me like what part you want me to explain again. Um, well, it seems like most of you understand the explanation. So like the basic concept here is that we have an algorithm that efficiently computes the GCD, and it requires just like some simple division and modulus, operations, right? So this is pretty simple. So, but eventually we will extend this and use this to compute not just like the GCD, but other numbers that could be of interest in like the different problems that we're trying to solve. So before we do that, though, we should cover, I think it's Bezout's identity. Not sure how to say it, but basically the identity is that for the smallest positive integer that's like a linear combination of x and y, which is ax plus by, is the GCD of x and y. And we can prove this, but let me just make sure. I mean, do you guys understand like what the statement is? Basically, we're saying like of all the linear combinations of x and y, the smallest one has to be the GCD of x and y. Okay, and yeah, so the proof goes as follows. So we let m be the smallest number, right? So this must exist. M is so we can write m as ux plus vy, and since x and y are both divisible by g, then any linear combination of those two numbers must also be divisible by g. So m must be divisible by g, right? And since m is divisible by g, we know that m has to be greater than or equal to g, right? And now we also know that when we divide x by m, and the remainder that we get, right, has to be a linear combination of x and y, right? Because x equals to qm plus r. Q is an integer, so x minus qm is just a linear combination of x and y. So r is a linear combination of x and y, but we also know r is less than m, since r is the remainder when we divided x by m. So if r is smaller than m and a linear combination of x and y, but m is the smallest linear combination, so smallest positive linear combination, then r has to be 0, right? And that implies that m divides x. So now we know that m must be divisible by g. So m is at least as big as g. M is greater than or equal to g, and m divides x. And also this proof that I did for like m divides x can also be done for y. So m also by like symmetry. So m also divides y. So m divides x, m divides y. M is greater than or equal to g, right? But if m was bigger than g, then m would have to be the greatest common divisor. So m must equal g. M is the greatest common divisor. Oh, that makes sense. Does anyone have any questions? As long as you understand the statement here, that's the most important part. Basically, we're saying that when you have a GCD, we can find some linear combination of x and y that equals to the GCD. Okay, so now we want to extend the Euclidean algorithm, same algorithm we were using before, to compute u and v such that we have the linear combination that equals to the GCD. And the way we do that's the same is basically the same way, right? We again write x equals to a y plus r, and we get the base case if r equals 0. Then obviously we know the GCD is y, and we also know that u can be 0 and v can be 1, and then we have the numbers that satisfy the Bezout identity. Otherwise, we want to find C and D, right? Otherwise we can find C and D where cy plus dr is a GCD of xy because of the recursion property, and we know that r is smaller than y. R is smaller than y, so we can recurse and find C and D. And once we know C and D, we can just do some algebra and just rewrite what cy plus dr, like what that means, right? So we just substitute r equals x minus ay, and then we just rearrange it to find the corresponding like linear combination where we know that ux plus vy equals GCD xy. So this the term like at the bottom here, dx plus c minus ad times y equals to GCD xy. It's in the same form as ux plus vy is GCD of xy. So then we know the answer is d is equal to u, and c minus ad is equal to v. And so now what we've done is that we've changed the Euclidean algorithm to not just give us the GCD, but also give us the numbers such that we know what the linear combination needs to be to find that linear combination, what the linear combination is that equals to GCD. And this is pretty useful. So we'll go over some of the properties soon, but hopefully everyone understands this before we go further on. So let me know if you guys have any questions. You can tell me in chat or you can unmute yourself. I'll give you guys like a minute. All right, it seems like no one has any questions, so we'll go over some of the properties of this. So one thing is that you can find the mod inverse pretty easily, right? And what the mod inverse is like you're given a prime number, and what you want to do is you're given a prime number and x, which is like x is number that's not divisible by p, right? So x is in the field of p, and we want to find some y such that when we multiply x by y, we get 1 modulo p. And not only does this exist, but we can find it for any x. where x is like not divisible by p. So, and the way we do this is just using the same algorithm that we were talking about, where we find some u and v, such that ux plus vp equals 1. And this has to be true since we said that x is not divisible by p. So x and p, their GCD has to be 1. Since p doesn't have any factors, yeah. And since we know ux plus vp is equal to 1, then then we can take the modulo p of both sides, and we get that ux mod p is 1. So u is the mod inverse. Is that faster than using Fermat's little theorem? Is Fermat's little theorem where you do the exponentiation? I would think so, because this is just log n. Or if it is, yeah, I would think that it is, because Fermat's little theorem requires you to do, it's probably around the same actually, but I know that this is the main way, or the easiest way that people do in competitive programming. It's probably like the same runtime, since when you raise something to the power of a number, you can do it in log n steps. So yeah, so it's probably around the same. Also, there's this theorem called the Chinese remainder theorem, and what we want to do in this is that we're given okay, yeah. So we've given n and m, and and we're given a and b. So we want to find a number such that when we take x mod n, we get a, and we take x mod m, we get b. And there's some restrictions here. M and n have to be co-prime, and a and b have to be like less than m. A has to be less than m, and b has to be less than m. And if you're given this, then we can find a unique solution. So the way that we know that there is a unique solution is that if we have two solutions, then we know the difference of them would have to be divisible by both m and n. But that's not possible, since we restrict that the solution has to be less than mn, and mn are co-prime. Hopefully that makes sense. Maybe I'll explain it one more time. So we're given two numbers, m and n, right? Those must be co-prime. So since sorry, let me read in the chat. Okay, yeah, he always used Fermat.
I think we're just having a side discussion in the chat. It's not relevant exactly to what you're saying.
Okay, well, it's fine. We can talk about this. The way we know that's fine is that this is actually more useful is that Fermat's little theorem only works with like prime numbers, at least. That's what I think. This one, like sometimes if you're given like a field, sometimes you're given like a p is not just like a prime number. P can be like the product of two prime numbers. And if you're given some number where you're given some number that's not just that's not divisible by both the prime numbers, you can also find the mod inverse using this method. And yeah.
Yeah, like it's like if the modulus and the number you're trying to invert are relatively prime, then you run the Euclidean algorithm and get 1, and then you found the inverse. If they're not relatively prime, it's not invertible.
Right.
Yeah.
Right. Okay, so Chinese remainder theorem, we'll get back to that. So we're given two m and n that are co-prime, okay? And then we want to find some x that's less than mn, such that x mod n is a and x mod m is b. So the m and n and a and b are the parameters. So first of all, we need to prove that x is unique. Well, if it wasn't unique, then we would have two numbers, x and y, and if we took x minus y mod n, we would get 0, and x minus y mod m, we would get 0. So then x minus y would have to be divisible by mn, but that's only possible if x minus y is equal to 0, because we already said that m and n are coprime. Okay, so now we know that it's unique. So what we do is to find the solution for Chinese remainder theorem is we run the extended Euclidean algorithm on m and n. We find u and v. So say um plus vn equals 1. And then to find x, all we do is that we write aum plus bvn. And this should be a solution to the parameters that we were given. The way we know this is that we know that x like mod n, x mod n is aum mod n, and we also know that um mod n is 1, right? Since we know that um plus vn equals 1, right? So x mod n is a. Yeah. And by symmetry, it's also x mod m is b. And so here we only showed where m and n are coprime, but if you look online, you can find how to do it with all mn, where m and n are not coprime. But in those cases, if m and n are not coprime, there does not have to be a solution for any a and b. Here there is a solution for any a and b, but that may not be true if m and n are not coprime. And we won't talk about this, but you can look it up. And just like there are like extended Chinese remainder theorem, like algorithms that solve not just this case, but the general case. Hopefully this makes sense. Does anyone have any questions? If not, here's the code for the extended GCD algorithm, and also the code for the mod inverse. So the mod inverse is pretty simple if you have the extended GCD algorithm already implemented. Yeah. Yeah, so this is actually done not recursively like I talked about, but this is actually done procedurally, iteratively. It's not much of a difference. All it is that you just convert the recursion to a simple while loop, and you just keep running that loop until you find until you reach that base case, right? And this is the Chinese remainder theorem. So this is done not just with like two numbers, but this is actually done with I think so this is done with, this one takes in a list of n and a list of a. So you don't have to reduce your input to a bunch of like function calls with just two parameters. This one takes in like an arbitrary amount of inputs. Yeah. All right. Wait. Let me just launch the poll. Does anyone want me to go over something that I talked about that wasn't clear? Let me relaunch this. Want me to explain something again? If you do want me to explain something again, can you just tell me what you want me to explain again?
I'd imagine like probably most people haven't really seen Chinese remainder theorem. That might be good to go over again. I don't know.
All right, yeah, I can go over that again. Okay, so let's see. Okay, yeah, so the Chinese remainder theorem is we're given basically, well, here I made it simpler just because it's a little complicated taking it at the first when you first see it. So we're just given two numbers, m and n, that are co-prime, and a and b, which are numbers that a is less than n and m and b is less than m. And what we want to do is we want to find a number such that x mod n is a and x mod m is b. If that makes sense. I mean, I guess I could give an example, like just like m and n could be like 5 and 7, and then like a and b would have to be like less than 5 and 7. So like you could find like you want to find like a number such that x mod 5 is 3 and x mod 7 is 4, right? So that would be like a instance of the Chinese remainder theorem problem. You want to find a number such that x mod 5 is 3 and x mod 7 is 4, and we can guarantee this exists because of like this construction that we've given. Since 5 and 7 are co-prime, you can find u times 5 plus v times 7, which equals to 1. We can let u be 3 and then v be minus 2, right? Because 3 times 5 is 15 and minus 2 times 7 is 14. So 15 minus 14 is 1. Yeah, so that's like an example. And then you would just multiply the x is 3, sorry, x is 4 times 3 plus 3 times minus 2. So that would be 6. Or sorry, I think I messed up. Yeah, 1 sec. Oh yeah, I messed up. So it's 4 times 3 times 5 plus 3 times minus 2 times 7, and if you multiply that out, you get 60 minus, you get 18. And yeah, and we can check that works. Because 18 mod 5 is 3 and 18 mod 7 is 4. So yeah, so that would be an example of how the Chinese remainder theorem works. And it's pretty simple in this case where we have m and n are co-prime, and yeah. And like if you look online, you'll find like examples. You'll find Chinese remainder theorem like not extends to an arbitrary amount of m and n. So you could be given a series of numbers, and that you have to find like the modulo of, and it has to be, and like you could be like 10 constraints, and then you just have to find like an x that satisfies all those 10 constraints. And these constraints don't, like the numbers don't even have to be co-prime, but when they're not co-prime, it may not always exist. But for now, I think like just understanding this example is good enough, and the other ones are not like too much more complicated. And I'm sure like when you're given the opportunity, if you understand this, then generalizing it further won't be too hard. Yeah. Okay. So hopefully that's good. Otherwise, we'll continue. So yeah. So another topic I wanted to cover was like checking for prime numbers. So a simple way to check like a prime number, I'm sure the first thing you would think of is just trying every number from 2 to the square root of n, and checking if it divides the number, right? And since we know that division is like constant, is a constant time, as long as like the n is not too big, then it's just squared n time. Yeah, so this is pretty simple. I won't talk too much more about this. If you want something more like faster, where we try to find all prime numbers from 2 to n, we can use this sieve method. And this actually has like n log n, yeah, n log n time. And yeah, so that I'll go over the algorithm. You start off by creating a Boolean array with a size n, and oh sorry, I meant it should be initialized to false, initialized to true. Yeah, let me change that real quick. That's my mistake. Oh, so okay. Hopefully you can see it now. Yeah. So that was a mistake. Yeah. So you initialize the array to true, and what you do is you from 2 to n, to the squared n, we run this run the inner for loop, because we go from I squared to n, and in increments of I we mark a of v false. And what we're basically doing here is we're saying, like, for each number we mark all its multiples as false, right? So like when I is 2, we're marking all even numbers greater than 4 false, right? Because they're not prime numbers. And then like for 3, we're marking all numbers divisible by 3 false. Um, and like the reason we only need to start from I squared, it's like a simple speed up, since we're all basically just checking, like we like basically if you're given a composite number n, then it must have like some number that divides into it that's less than squared n, so then that number will mark it false even if you started from I squared. I hope that makes sense. Like basically, like if you have like a number like uh, yeah, so if you have a number like 18, right, or sorry, if you trying to think of a good example, but if you have like a number like 9, right, so 9 is divisible by 3, right, so we can, if we when I is 3, we start at 9, so we mark it false. If you have a number like 39, 3 will mark it false. So the smallest divisor of any number will has to be less than the square root of that number. So therefore, it's like safe to start at I squared and mark those increments from I squared and beyond as false instead of starting at I. And then once we've done all of that, then every composite number will be marked false, and every prime number will remain as true. And then therefore, then after that, all we have all like the prime numbers. Hopefully that makes sense. Then we can analyze the runtime, right? So if you're marking like all even numbers as false, that's like there's like n over 2 even numbers, then there's like n over 3 numbers divisible by 3, and so on. So we did that. So it's just n over 2 plus n over 3 plus n over 4, all the way to like n over squared n, and this is like similar to like the harmonic series. It's just like, so the runtime is just like n log n. Does anyone have any questions? You would use this like pretty, like you would use this if you want to find all the prime numbers from 2 to n. If you just want to find if one number is prime or not, like you just want to find if n is prime or not, then the simple prime check definitely is a lot faster. This one takes like n log n time, but it gives you all the prime numbers from 2 to n.
Shouldn't it be like a bit faster? Because like you get to skip all the numbers that are composite when you're doing the check, right?
Faster than the simple like check, you saying?
Just like, yeah, isn't it like n over 2 plus n over 3 plus n over 5 plus n over 7? I guess maybe that's like not a huge
Yeah.
jump. I feel like it's actually like asymptotically faster than n log n. It's like maybe something complicated, but I think it's faster than n log n.
I'll have to look it up, but I think like there are enough prime numbers at least for that. It might be like n log n, but I think like n log n is obviously like an upper bound because this is n over 2 plus n over 3, right? Because n log n is approximately n over 2 plus n over 3 all the way to like n over n. This is definitely smaller than that. It might
Yeah,
be
I
smaller.
googled and it's n log n.
Oh, okay. Yeah. Yeah, so I guess that comes from the fact that like prime numbers are logarithmic, like are like like the frequency of prime numbers is like 1 over log n, so
Yeah,
that
like
would
the
make
nth
sense.
prime number is like around n log n. So it's like n times sum over like 1 over n log n, and that's like log. Yeah.
Yeah. And in that case, like to get that like speed up, I guess you would have to make sure that like a of I is true before you start marking its increments as false, its multiples as false. Yeah. So anyone else has any questions? I can go over this is just the code for like the sieve. You create the array and then in the and then you just look at from n in like for like all the numbers less than the square root, you just mark its multiples as false, and then in the end you just return all the numbers that remain as true. Yeah, pretty simple. And oh, I included twice, but I think that's it. I also included a link here to the Miller-Rabin test. It's not very, I mean, I don't think it's very useful to understand. It is interesting, and but it won't be used as much in like competitive programming, other than like the internal part. You might want to like have it as like a reference material, but it is like it's basically just like a very fast prime checker that uses like randomness to determine if a number is prime, and there are like some tricks you can do to make sure that the test is actually deterministic and like less than some like upper bound. So if you have some time or you need like a really fast prime check, then you may want to look into this, but I'm not going to cover it. And that's it. I think the attendance code is not working yet. I'll ask Justin about that. But does anyone have any questions before we move on to like the contest? No. Okay, I'll stop the recording then. And let's see.